Hello viewers, this is Dr. Aisha Nazuk here with today's topic, which is Spearman rank correlation coefficient. So those viewers who are watching this video as maybe the first video on this channel, that is the Rao Hub, it's highly recommended that you watch all other videos uploaded specifically in the playlist of statistics. Okay, so if you go to the channel Rao Hub, there are different playlists. This particular playlist, that the statistics lecture, is relevant to all the students who are pursuing statistical skills or pursuing such a course which require introductory level statistics skills. Specifically, currently I'm recording these lecture for the students enrolled an Introduction to Statistics course in an undergrad degree in economics at NUST. But these lecture resources could be used by anyone who is interested to get acquainted with the introductory level concepts of statistics. Okay, so the channel name is Rao Hub. I'll spell for you as well. R-A-O Rao H-U-B Hub, Rao Hub. Here is the name as well, right? Rao Hub. So on Rao Hub, the playlist statistics lecture is relevant for all those students who are interested to get acquainted with the concept with the introductory level concepts of statistics. Okay, so if you're watching this video, it's highly recommended that you watch the previous videos as well. Specifically, this video, Pearson correlation coefficient, is highly relevant with today's lecture or today's video. Okay. So now we start today's topic, which is Spearman rank correlation coefficient. Okay, just a quick recap. What is the purpose of correlation? Correlation is a measure of linear association between two random variables, right? This is what we learned in the last lecture as well. So that's why I'm referring again to that video that you watch that video as well. A quick one-liner purpose of correlation is to see the linear association between two random variables. Okay, so this specific form of correlation coefficient is called Spearman rank correlation coefficient, and this is actually an alternative form of the Pearson correlation coefficient that we did in the last lecture. So Pearson correlation coefficient, if you go and see the formula, it's based on moments, or in simple terms, it is based on sample arithmetic mean and sample standard deviation. But this formula, the rank correlation coefficient formula, is a little bit different, because you know that when the variables are not purely quantitative, you cannot or you should not calculate arithmetic mean and standard deviation. So then what to do if there are some variables that are in the form of some rankings, right? How to see association between those type of variables. So that is what we are going to cover in today's lecture. So before I introduce the formula for the rank correlation coefficient, let's see the two important assumptions. First one is that the two variables that are either ordinal or pure quantitative. Now you must be thinking that I just introduced, or I just mentioned that the rank correlation coefficient is for the variables that are ranked or that are ordinal, right? Ordinal or ranked variable, one and the same thing. So why am I saying that it could be used for pure quantitative data as well? Actually, the answer is simple. It's not that technical. The answer is, even if we have pure quantitative data and some of the assumptions of the ordinary correlation coefficient are not met, then we can apply the rank correlation coefficient on that type of data as well, right? What I'm saying, for example, if the data is skewed, that is, we have an outlier, So we can apply the rank correlation coefficient on that type of a data. Okay, so when the assumptions of the Pearson correlation coefficient are violated, for example, we have a skewed data, which is an exact opposite of symmetric data. So if we have a skewed data, we can apply the rank correlation coefficient. Okay, so what are the assumptions as we were discussing of the rank correlation coefficient? The first assumption we studied was like the two variables are either ordinal, that is, both are either on ranking form, or both are purely quantitative. Even then we can apply the rank correlation coefficient formula. The second assumption, this you studied in the last lecture as well, because this assumption is same. It's no matter which type of correlation coefficient you are calculating, whether the simple one or the ranked one, this assumption has to be met. That is, there should be a monotonic relationship between two variables. So what's a monotonic relationship? We did in the last lecture video as well. Just a quick recap, that a monotonic relationship is one which is either increasing or decreasing, but not both. Okay? For example, if you look at this type of a graph, this is linear, like the points are clustered around a straight line, and it's monotonically decreasing. This is non-linear because the points are clustered around a curve. Like if we draw a curve, this is going to be like this, but it's monotonic because it's overall increasing pattern. So this is monotonic linear, this is monotonic non-linear. Okay, so the assumption is that there should be a monotonic relationship between two variables. Okay, now the question arises, can I apply correlation on this type of a diagram? Yes, you can, because this is monotonically decreasing and it's linear as well. This one, this is monotonically increasing and linear as well. Okay, go ahead, apply the correlation coefficient. This one, this is non-monotonic, a mix of increasing and decreasing. So you should not apply correlation coefficient. If you watch the previous video, there's a specific example of this type of a graph and a detailed numerical example, how to handle that type of a data. Okay, what if we have this type of a scatter plot between the two random variables? Now this is non-linear, right? But this is monotonic. I can apply correlation coefficient on this type of a data because no matter it is non-linear, but the degree of non-linearity, that is the curvature or the bend in this curve, is not too much, right? So if I calculate the correlation coefficient, that coefficient will give me a linear approximation of this type of a data, right? Like that correlation will be studying the linear part of this diagram only. Okay? Okay, so now we have a numerical example for ranked correlation coefficient. Let's say we have data of some countries, we have their GNP, which is the gross national product, and we have percentage of adult literacy, and we want to see whether the countries where the educational status or literacy is better, are their national income or the GNP per capita is high or not. So let's calculate the correlation coefficient, right? Okay, so how to calculate the ranked correlation coefficient between these two variables? Okay, how to calculate? So you know that Spearman rank correlation coefficient can only be used with ordinal data, or if you have a ordinary quantitative data, you have to convert it in the form of ordinal, that is, you have to convert it in the form of ranking. How to do that? Okay, so what we do is we call one of the variable as x and the other as y. And that is purely arbitrary. I mean, you can call any one of these as x. So let's say I call GNP as x and percentage of adult literacy as y. Now I want to find out rank of x, rank of y, and there are some other columns that you will understand in the coming slides. Okay, so how to rank? If you see, you can actually do the ranking in any way, like either in ascending order or in descending order, right? But if you do the ranking of X in ascending order, then you should also do the ranking of Y in ascending order. I mean, it's not that you can't do mix, like ascending order of X and descending of order of Y, that will be incorrect. So either follow ascending or descending, both in X and Y. So if I see 210 is the lowest value in X and I call it 1. The next one is 290, I call it 2, and so on. So that's how rank of X will be assigned. So we have data on rank of X from the lowest to highest value. I have ranked these. Now I have to rank Y as well. Okay. So how to rank Y? The minimum value in Y. So why I'm looking at the minimum value? Because when I was ranking X, I assigned 1 to the minimum value. So similarly for the Y variable, the minimum value is 34.5. So I will assign 1 to the minimum value. Okay, similarly, the next value is 39.7, so the assigned rank is 2, and so on. I will calculate or find out all the ranks for the Y variable as well. Now, according to the formula, I have to calculate the difference between these two ranks and then square up. Like the difference between rank of Y and rank of X is called D, and then we square up because that's a requirement of the formula. You'll see the formula shortly. So I calculate the difference between ranks and I square them and I find the sum of the squared ranks, right? And n is the number of pairs. So how many pairs we have for X and Y? You see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's why n is 10. Okay, so now I have n is 10, sum of d square is 44, so I'll simply switch in this formula, 1 minus 6 times summation d square divided by n cube minus n. So I switch on the values in this formula and I'll get the value 0.73. So that means it's a fairly, you could say, strong correlation between GNP and adult literacy. And the correlation is positive, which means the countries where the literate people are more, they are expected to have more value of GNP per capita, right? So that was one simple example of ranked correlation coefficient. Now I will introduce another numerical for the same concept, but we will have a little bit of a problem in that the ranking will be tied. So how do they see that? For example, if I have this type of a data and I want to see whether there are any correlation between marks in English and marks in maths, so what I do is, first of all, similar to what we did just now, I calculate the ranks. And for example, this time I assign one value to the highest. So if you see the English marks column, the highest value is 80. So to 80, I have assigned the rank 1. The next highest value is 76, so I've assigned it the value 2. Then the next highest is 75, I've assigned it 3. Then the next highest value is 71 and I've assigned it a rank of 4. Then the next highest value is 62. But the problem is 62 is occurring here as well as here. So we have problem of tied rank, like the two values, they have a tie in ranking. So after 4, which is the next rank that was to be assigned? It must have been 5. But the problem is 62 is at rank 5, but then we have another 62. So had these values been different, what we would have done is to assign a 5 here and 6 here, right? Let me type. Had these values been different, I would have given it a 5 and this one 6. But now these two values are same. So what I'm going to do is I will calculate the average of 5 and 6 and that comes out to be 5.5. Okay, I'm sorry, it's a little bit of a correction that is required. The rank at 5 is 64. So this one might have been 6 and this one 7, right? Just for the sake of clarity, I repeat once again. Highest value 80, rank is 1. Next highest 76, rank is 2. Next highest 75, rank is 3. Next highest 71, rank is 4. Next highest 64, rank is 5. Now the next highest is 62, but it's being repeated. So we have assigned it a rank of 6.5 because had these 62 value that is occurring twice here, had these two values been different, we would have given it 6 and 7. But now because these are same, so I'm giving them a rank of the average of 6 and 7, which comes out to be 6.5, right? So theoretically, we have consumed data till 7. So the next rank will be 8, right? So that's how we have calculated rank in the case of tied rank. And similarly, for the maths marks, I will calculate ranks here, which are simple because there are no ties in this column. And then similarly, I'll calculate the difference between these two ranks, like 9 minus 4 is 5, 3 minus 2 is 1. And then I square these deviations and proceed further, just switch on the values in the formula and find out that there is a fairly strong positive association between marks in English and marks in maths. Okay? So now we start the next topic for today, which is the concept of relative variation. Okay. By the way, if you're a bit tired about just finishing one concept and you think you need a break before starting to understand the next concept, you can pause the video and you can watch after like 5 or 10 minutes so that you'll be in a fresh state of mind. Okay, so the next topic is the concept of relative variation. Suppose that we have two or more data sets and we want to compare the degree of scatter in each, right? If you can recall that how we calculate the variation in a single data. We calculate the variance of their data or the standard deviation. Because the standard deviation is in same unit as in the data. Like if the data is in kgs, standard deviation will be in kgs. So what if we have to compare the variation in two or more data sets that can have different units, that can have different inherent factors when the data was being collected? Like one example, if we have one data which is weight in kgs and another data which is height in inches. Now we cannot compare the standard deviation of these two data sets directly because the units are different. So in this particular example, just because the units of the data are different, you cannot use standard deviation to compare the variation in these two data sets. Now consider another example. Suppose that a quiz was being conducted in two different sections of a class. In section A, suppose the invigilator was very strict, whereas in section B, the invigilator was lenient. He was not really looking at the students whether they are trying to copy other people's answers or not, or are they involved in academic dishonesty or not. So the marks scored by the two sections, they are dependent upon the invigilator's quality or trait. So we cannot compare the standard deviation of marks in these two sections although the units are same, both classes are being graded, let's say, out of 20. But just because the invigilator was different in these two sections, we cannot and we should not use standard deviation for comparison of variation in these two data sets. So this is an example where due to data inherent factors, the two data sets, they become so different that we cannot use standard deviation for comparison of variation in the two data sets. So to cut short, you should never use standard deviation for comparison of variation in two or more data sets. So here we have another example. We have two data sets. First data is about price of a carton of milk, and the second data is demand of the carton. So you know that data 1 or the price is in PKR, suppose, like Pakistani rupee. And data 2 is in number of cartons, because it's the demand of cartons. So how many cartons are being purchased? So we cannot use standard deviation to compare variation in data 1 and data 2, right? So what to do if we have two or more data sets and we want to compare variation? Then we should use coefficient of variation. And coefficient of variation, or simply abbreviated as COV, is actually standard deviation divided by the mean into 100, right? What am I saying? That you calculate standard deviation of the data, mean of the data, divide these two values and multiply by 100. Now coefficient of variation is a standard, or you could say unit free statistic. Why? Because the problem that I was just mentioning, difference in data units and difference in data inherent scenarios or factors, those problems are represented both in standard deviation and in mean. So what happened? When in the denominator we have some problem impact, even in the numerator we have the same problem impact, so it's cancelled out and coefficient of variation becomes unit free value, right? So if we have to compare two or more data sets, what is that being advised is you calculate coefficient of variation, and the data whose coefficient of variation is higher is said to have more variation, right? So for example, if we want to compare the average IQs of students of NUST with students of Preston University, by the way, these are the names of two universities of Pakistan. So it's for those viewers who are watching the video, but they are not residents of Pakistan. So it's for their information. So let's say if we want to compare the average IQ of students of NUST with students of Preston University, then we will expect that higher numbers will be in NUST dataset. Why am I saying so without sounding judgmental? What I'm saying is generally the merit of NUST is higher. NUST University is more selective in its admission process as compared to Preston University. So the average IQ of NUST students is on average or generally higher than the students in Preston University. I'm not sounding judgmental, and I'm just talking about the general trends. So let's say we want to compare variation in the two data sets. So what we will be doing is we will be calculating standard deviation and arithmetic mean in both the data sets and compare them. And for example, if standard deviation in data 1 is this value to 605 and the mean is this, you just divide and you get COV. So now if you have the coefficient of variation of both the data sets, so data 2, you see its coefficient of variation is much smaller than the coefficient of variation of data 1. Now there's an interesting thing here. If you see the standard deviation of data 2, see this is standard deviation here in numerator. So if you see the standard deviation of data 2, it is much higher. So if I compare on the basis of standard deviation, it will be totally wrong, because it is dependent upon the scenario under which the data was collected, right? I think this part, which I'm just commenting, that the standard deviation of data 2 is higher or not, I think it's better to ignore it currently, because there was some in this last line there was a typo, so I apologize for that. Just focus on the coefficient of variation. Forget about the line that I just spoke about, the standard deviation. So the coefficient of variation of data 1 is much higher than the coefficient of variation of data 2. So we will say that there is more variation in data 1, right? So from exam point of view, if you are given two data sets and you are being asked that which data has more variation, you should separately calculate the standard deviation and mean of both data sets, and then you should calculate their coefficient of variation once again separately, that is first for data 1 and then for data 2, and then compare the final answers of coefficient of variation. So the data whose coefficient of variation is higher is said to have more variation, right? So COV of data 1, as we just saw here, this COV, coefficient of variation of data 1, is higher than coefficient of variation of data 2. So therefore, data 2 has, data 1 has more variation. Pardon for some of the typographical error in today's video. So focus on what I'm speaking. Data 1 has more variation, right? Data 1 has more variation. So just forget about the other things that are mentioned here. Just conclude today's lecture here on this note, that data 1 has more variation. So this type of a concept is applied when we have to compare variation in two or more data sets, right? So with this note, I end today's video, and if you have any queries, I will, in the comment section of the video, I will also mention my email ID and the channel Facebook page as well. This is for the general viewers. For those students who are specifically registered at the NUST University in Statistics course, they can always reach me out through the class WhatsApp group that we are actively managing, right? So for now, I end today's lecture and we will meet in the next video. Thank you.